Good evening. Thank you all for coming and welcome to the first session of 2013 Darwin on the Palouse. We're really happy that you've all come out to join us tonight. I'm Tyler Palmer. I'm the president of the Humanists of the Palouse. We're one of the organizations that puts this on and makes up the Palouse Coalition of Reason. A year ago, we set out to have a small Darwin Day celebration. We hoped to have a couple local speakers, maybe a couple bottles of wine, and enjoy some education. And it kind of blossomed on us, and a lot of that was due to the support of the community. And so we decided we'd give it another whirl, and we're very happy to be here again having another Darwin on the Palouse. An event like this takes a lot of work, especially since it's purely volunteer organizations putting it on. So there are a few people I'd like to thank as we get started. There are many members of the Humanists of the Palouse that have put in hundreds of hours trying to put this together. Free Thought Moscow, which is the student organization with the University of Idaho, and the Secular Cougs, WSU, which is the organization here, the student organization with Washington State University. I'd also like to thank the American Humanist Association for their support of our event, and the facility staff here at the university who are always so helpful as we try and put these on. Also, very grateful for some local donors whose generosity really makes this entire thing possible. And so we're really happy to be able to provide this. We really live in an era with unprecedented access to information. And it's an era where ignorance on almost any topic can only be ascribed to apathy or dogma. And in such an era, we usually use this power to watch videos of cats or watch people fall off their bikes online. But tonight we'd like to take a moment to celebrate our mutual quest for understanding. Take a moment to celebrate intelligence, celebrate reason, and celebrate knowledge. Charles Darwin said, "Doing what little one can to increase the general stock of knowledge is as respectable an object of life as anyone can in all likelihood pursue." And we're happy to have two speakers here with us tonight that have been in that pursuit. And we're happy that all of you are here to join with us as we listen to the presentations that they have. In just a moment, I'm going to ask Tony Smith, an officer with the Secular Cougs, to introduce our first speaker, Dr. Frank Brown. Following Dr. Brown's presentation, Lowell Bushy, a member of the Humanists of the Palouse, will present Dr. Valerie Tirico. And if time permits, we'll have a brief question and answer period after the presentations. So once again, thank you for your attendance, and we look forward to a great weekend. Thank you.
Well, first of all, Tyler only got one thing wrong, and that's that I'm not actually an officer. But other than that, he was right on. If you're like me, you grew up watching a lot of nature documentaries about fossils and the history of life on Earth. And you may have heard of the Leakey family, who, if you are a fan of using Google like I am, saw that yesterday Mary Leakey's 100th birthday was honored. And that is very fitting, because today our first speaker is someone who has worked closely with the Leakey family on dating the fossils that they have found. Dr. Frank Brown was awarded his PhD in geology from the University of California, Berkeley in 1971. He joined the faculty of the University of Utah the same year, becoming full professor by 1980, chair of the geology department by 1988, and dean of the colleges of mines and earth sciences by 1991, a position he still holds. His first research trip to Africa was in 1966, and the important thing to remember about this trip is that, from what I've researched on him, it was solo. His advisor basically sent him there alone, which nowadays I would hope that no advisor would send someone into a situation like that, but sometimes that may still happen. He has made dozens of more trips since, studying the geology of East Africa, and has worked closely with the Leakey family since 1980, helping to date the early hominid fossils that they have found with radiometric dating and sediment dating, and helping to flesh out the human family tree. His work has been featured in such magazines as National Geographic and Life. Aside from his field of study, he's also a very fascinating individual, and I wish I actually had more time up here to talk about him, because in researching him, I read about quite a number of interesting stories, including the incident with the carjacker in France, and an incident with a cobra while he was writing in his journal, which I will have to ask him about later. He speaks several languages. He speaks fluent German, Swahili, Amharic, Turkana, and Kikuyu. And without further ado, Dr. Frank Brown.
Thank you very much for inviting me up here. I'm very pleased to be here. I have had an absolutely magnificent life. I went off, as I say, to a very terrible time in 1966. The Kenya police almost didn't let me go north because a British student had just died on the Maji Escarpment a little bit farther north from where I went. But in that year, I think I fell in love with Africa and its geology, and I've been back every year since, and next Wednesday I'll be on a plane again to help them out with the stratigraphic problem in the younger part of the sequence. Now, as my introducer mentioned, the Google banner yesterday, it was Mary Leakey's 100th birthday, and they actually put Mary Leakey with her Dalmatian dogs down there at Olduvai on, and that's quite a tribute. I don't think I certainly will never be a Google banner poster child. So what I want to talk about today is Darwin's difficulties. Darwin's difficulties were time and fossils, because he wrote about what he thought about the evolution of man, but he had no good notion of geologic time. He had a better notion than geologists did at the time. And there were no fossils of early man except for the Neanderthal skeleton. One of the statements that Darwin made that I have always liked is he said, "It has often and confidently been asserted that man's origin can never be known, but ignorance more frequently begets confidence than does knowledge. It is those who know little, and not those who know much, who so positively assert that this or that problem will never be solved by science." At any rate, when Origin of Species was written, for example, there were no fossils of early man, or almost no fossils of early man. Geologic time was very poorly understood. You probably know that Darwin, after being told that the basalt at Arthur's Seat was precipitated in the universal ocean by a Mr. Jameson, probably one of my ancestors, he made the statement that at that time he determined never to attend to the science of geology. Radioactivity was unknown at that time, and genetics was unknown. Darwin, in writing The Origin of Species and even in The Descent of Man, wrote about the strong principle of inheritance. He had some inkling that something genetic was going on, but we knew nothing about genes yet. Well, today there are hundreds of fossils of early man. It's probably pushing 1,000 now. Geologic time is very well understood. Radioactive elements that decay to daughter products allow the dating of geologic events, and the very presence of radioactivity in the Earth removes objections to an old Earth. The objection was, it came actually from Lord Kelvin, who was the highest authority in science then living, who modeled the Earth as once a molten sphere and said it would take, at first he said 400 million years to cool to its present temperature, then he said it was 200 million years, then he said it was 40 million years, and then he said it was 20 million years, and to rub salt into the wounds, he said of the geologists, if you cannot put numbers on something, you know nothing about it. Well, you can put numbers on things, but if those numbers are founded on faulty assumptions, you really know nothing about what you're talking about either. So, the fact that radioactivity creates heat in the Earth meant that all of Kelvin's calculations were wrong. Well, genetics today, of course, is well understood, and it provides prime evidence for the relatedness of all living things. Now, what I want to do tonight is talk about this place, and I don't have a pointer, but you see the guy shaped like Ireland there. That's Lake Victoria, all right? And then to the upper right of that is a long lake. That is Lake Turkana. It's the largest desert lake in the world. It's about 200 kilometers long, about 150 miles, if you like. You'll notice the green. The green is all vegetation, and you'll notice that there's very little around Lake Turkana. It's a very arid area. It lies at an elevation only about 500 meters above sea level, about 1,500 feet, right? It's related to the Rift Valley of East Africa, but it's not really part of the Rift. And it gets its water, that lake gets its water mainly from the Ethiopian highlands. Now, I could run down there and try to point out some things. Far to the south, to the southeast of Lake Victoria, is where Olduvai Gorge is. That's where Mary worked. The big mountain there is Kilimanjaro. Up to the north, just off the north end of that image, is Hadar, where Don Johanson found Lucy. Don Johanson was also a person who cut his teeth in the Turkana Basin working with Clark Howell. Now, what's important about desert regions is that you can essentially see all of the rocks. The water, remember, comes from the highlands, okay? And the geologic record in Turkana records both local events and distant events, and very importantly, as you see a bit later, it shares a divide with the Nile River. All of the water from Lake Victoria goes into Lake Albert and then down to the White Nile, and the Omo River that flows into the north end of Lake Turkana shares a divide with the Blue Nile. Right? So now, well, this is where I landed I didn't quite land there. It took me 3 days to drive there from Nairobi. This is where I started my work in 1966 in the Shungura Formation in southern Ethiopia. It was done in preparation for a major paleontological expedition in 1967. And what is important about the Shungura Formation, as I think you can see very nicely here, is that you can see every foot, every meter of sediment that is exposed. It means that you have you can write a very complete story of the geology of this area. Now, what Clark Howell wanted, he came out to Berkeley and looked for a student to go up to Ethiopia, and I did that. What he wanted was to know how old these beds were before he sent the paleontologists in to collect fossils there. So I spent a summer there before the rest of the people. I put an outline of Utah on here. I tried Idaho. I've done it in the next slide. I put an outline of Utah on because it gives you an idea of the size of the Turkana Basin and why we have worked there for nearly 50 years. In fact, Ehrenberg was there in the 1930s and collected tons of fossils that are in France. Bourg des Beaux-Arts was there in 1906. He didn't get back, but he was actually the beginning because when he got to the Congo River, he died, but his notebooks and the few fossils that he had came back, which is why Ehrenberg went in the 1930s, and Ehrenberg going in the 1930s is why Clark Howell went in the 1960s after Mary Leakey found Synthesizing, now Australopithecus boisei, at Olduvai Gorge. Well, these various areas, it's not important where they are. What I want to get across to you is that the anthropologists will find something maybe at the north end up there, and they want to know how it relates in time to something at the south end. And that's really our job as geologists. We tend to stay away from most of the questions will always be about the early man fossils. That's not what I do. What I do is date them. I work on the environments of deposition, and most recently we've been able to show that for the past 4 million years, it has been very hot there. And this is here's Idaho superimposed on it, so you have an idea. I suppose I should have done Washington because Idaho's across the border in Moscow there. These are some of the names that you will see. Ilaret, Shungura Formation, where we began. the Kibish Formation, where we spent the next year, Nariakotame, the place where we have the only 1.5 million-year-old skeleton that yet exists of early man. Lomekwi, a little bit farther south there, where Kenyanthropus comes from, Alia Bay, Lothagam, and Kanapoi, where we have Australopithecus and afarensis, and then Kubifora, which beginning in 1968, under Richard Leakey's direction, was the site where so many fossil skulls came out that we learned an immense amount more in about 3 short years, probably than we have since. Right? Now, there were all sorts of fossils there. These 2 giraffe leg bones give you an idea what the preservation is like, all right? But we also have fantastically preserved baboon crania and postcranials. We also have pigs, and these pigs are, you must never, don't fight with pigs if you're a geologist. If the paleontologists tell you that something is old because of a pig they have, they are right, and you are wrong, because the pigs evolved very beautifully through time, and we can always tell where we are in time once you know the pigs pretty well. And then the most abundant fossils we have, aside from hippos, are these bovids, or antelopes, if you like, and they tell us a lot about the ancient environment there, right? So, what I want to do tonight, is talk about relative time, first of all, their superposition, and the fossils themselves. Now, superposition is the simplest thing in the world, and if you're students here, you know that if you toss your clothes on the floor in your room, the ones that are on the bottom were there before the ones came down on top of them, right? And if you're not a student and you bring your mail in every day and you don't look at it until Friday, then the mail on the bottom is the oldest and the mail on the top is the youngest, all right? It's one of the simplest but one of the most important laws in all of geology. Now, the fossils themselves I've already mentioned. The pigs tell you where they are, the kind of elephants you have, the kind of bovids, and so on. Once you get to know the fossils, you have an idea of the age, but you can't put numbers on it. Now, putting numbers on time can be done in many ways, and I'll start with annual layers, because all you have to do to count time there is simply count, all right? And everybody can do that, all right? Then there are other cyclic phenomena, and I'll talk very briefly about the Milankovitch periodicities in climate changes. Then I'll talk about isotopic dating methods. These are the ones that you mostly hear about. Most people think of carbon-14, but carbon-14 dating only goes back to about 50,000 years, and we have things that are in the millions of years old, so we need a method that we call potassium-argon, or equivalently, argon-4039. And then there are secondary calibrated methods that can also be applied. So, here's an example of the Kibish Formation. This particular chunk of section is about 100,000 years old. That machete is about 60 centimeters high, roughly 2 feet. You might think that each of these layers represented an annual flood, all right? Now, it's all fine to think that, but how do you go about showing that it actually might be an annual flood? And one way that we could do it is by the fact that the magnetic field of the Earth varies with time. The magnetic pole is never quite in the same place year to year, and we know how fast the declination, for example, moves. So we took samples through this, starting at about -6 meters there, and going upward. You see there's a very regular change in declination through this laminated part. Well, the change in declination is 0.033 degrees per year, so that thin-bedded sequence by this measure should be deposited in 350,000 years, all right? If you simply count those in a number of sections, you count 245 to 360 years. So it's probably a very good guess that those are annual layers. Now, in fact, varv counting is tremendously important. It was Daguerre in the early part of the last century who had a stack of students counting varves in a glacial lake, and he knew the year that the last one formed was 1797. And he had his graduate students count over 12,000 varves. So he knew that the Earth had to be at least 10,000 years old. That is, had to be at least 12,000 years old, all right? Forget about the calendar years. And then we have varves in other places. We've got 3 million of them in the Green River Formation. We've got 18 million of them in the Castile. And so you can stack these things by superposition, so the Earth must be at least 20 million years old. This was incredibly important because to some people, 4004 BC is sort of a very, very special year. The calculation is actually wrong. If you go back and do it yourself, if you're good biblical scholars, you'll find out that's the case. All right? So we can count, all right? Now, the other thing that we can do is look at, in the tropics, it depends where you are on the Earth, but there are very regular changes in the orbit of the Earth, in how round it is, if you like, how circular it is, in the timing when the Earth is closest to the sun and farthest from the sun, whether that's at midwinter or midsummer, and also in the tilt of the Earth. And these have 3 different periods that interfere because they're non-integral multiples of one another. And you get this wonderful beat effect. But each of those little peaks is just 20,000 years long. That's 0.02 million years, all right? Now, we can actually use these, and sometimes when there is interference so that the amplitudes get very large, we get peculiar deposits in the Mediterranean Sea that we call sapropels. I'll show you those in a little bit, okay? Now, how can we see what's happening on land and look at what's happening in the oceans at the same time? Well, one way we can do it is by the dust load in the atmosphere. This is a picture taken near Lokitong. We were in a helicopter and had to get above this thing. It was a jet helicopter. If you run into heavy dust, it fills up the turbines and you are down 7,500 feet before we got over this dust cloud. This is the sort of stuff, you can see it on Google Earth. It moves off into the Atlantic, it moves off of the Horn of Africa into the Gulf of Aden, and it is cyclic. When lakes are high, there's very little dust. When lakes are low, there's lots of dust. And we can see this beautifully in deep sea cores in the Gulf of Aden. You see that little wiggly curve over there on the right, okay? Every one of those little bumps is 20,000 years, so 20, 40, 60, 80, 100, all right? Just count it. Well, I counted 5. If I count 50 of those peaks, I've got 1 million years, all right? Now, we had some volcanic ashes also that were distributed in these, and I'll come back to that point again, but the Tullamore Tuff had been dated, the Wargolo hadn't been dated, the Lomogol hadn't been dated, the Moiety hadn't been dated, and yet by looking at where they fell, simply counting those peaks, we go 0.02, 0.04, 0.06, we could say what their age was to the nearest 10,000 years, depending on where they fell in the cycle. Now, this was tremendously important because there was a huge fight between, not fight, it was an argument, it was a gentlemanly argument between the people at Hadar with Lucy, who thought Lucy was more than 3.5 million years old, and some of us who thought that she was much less than that because she was above this particular tuff called the Tullamore. Eventually they agreed that we were correct. Now, in the deep sea, you have essentially continuous sedimentation. Constantly, material is raining onto the bottom of the sea. But on land, we don't have that luxury. And I've shown you member 2 there and member 3 above it. And you see that was an old hill, very much like you have the hills here with material deposited on top of them. So what happened in this case, member 1 was deposited up to the base of member 2, then it was eroded, then you had member 2 deposited, and it was eroded, and then you had member 3 deposited, it was eroded, and then member 4 came down. And this is in the Kibish Formation. Well, what we need to figure out as geologists is how much time is on those erosional surfaces and how much time is actually represented by section, that is, sediments that you can get your hands on. Now, this, in a cartoon-like form, we have a 4-million-year-old basalt. The Inkalabong Formation is between 4 and 3.4 million years old. And then we have this member 1, which was eroded, member 2, which was eroded. It's a terribly complicated geology, a very messy map to have to make. And the Omo River is now eroding it all away again, all right? So we wonder how much time is represented and how much is lost in the erosional surfaces. And anyway, who gives a damn, right? Who cares, right? Well, this is why people cared, all right? In 1967, Richard Leakey, near his camp, collected a partial skeleton of an anatomically modern human. This is Homo sapiens. And 30 years later, people got interested in this. Nobody cared for 30 years. Well, they tried to find somebody to go back and show them where they got it, and I seem to be the last living person, except for Richard, whose legs, you probably know, were severed below, he's had them amputated below the knees because of a plane accident, probably sabotage. They wanted to know its age, all right? Well, I went with John Flegel from Stony Brook University. He said, can you show me where this thing came from? And I said, yeah, I can show you, John. And look at that, that distal femur there. That's the bottom of your thigh joins the knee, okay? Because we went there, and John didn't say it. Those are his feet for scale. John didn't say a word, but there's the chunk that was collected in 1967. And he said when we went there, he said, it doesn't look like the photos I've seen of it. I said, John, I'm sure this is the place. He put the upper piece of bone in his pocket at that time, took it back to the museum, and it glues on, this was 2001, it glues onto the piece that was collected in 1967. We had the right spot. This is a problem that you no longer have, and you students have to really understand how lucky you are. You can measure anything you want. You can locate yourself in GPS, and you know where you are for all time. Never, never, never write down waypoints in your notebook, though, because what happens is that your friend, maybe Lowell here, will borrow your GPS and need a few more waypoints, and so wipe out your memory. Instead, write down the latitude and longitude in your notebook while you're there, all right? That's very good advice, believe me, all right? Okay, so how do we get at this? Well, on the right-hand side there, that shows Lake Victoria, the big sort of Ireland-sized lake in Africa. It flows down to the Nile all the way to the Mediterranean Sea. And then you see Lake Turkana there, and you see that there's a divide, a drainage divide with the Nile, all right? Now, if you core off of Greece, just north of the Nile Delta, the sediment core, and I don't know if you've dealt with sediment cores, but these each are sections. It would stack one on top of another. You see they go black, white, black, white, black, white, black, white. Each of those black layers is a sapropel. It's an organic rich layer that is found on the bottom of the Mediterranean Sea. And the way these things form is that when there is a lot of rainfall coming out of the Ethiopian highlands, it puts a freshwater lid on top of the eastern Mediterranean, and so no oxygen can get there, and so you preserve organic material that falls to the bottom. Well, these sapropels are extremely well dated by literally decades of work in Europe, and we had 3 dates. We had an 8 to 12,000 year date at the top by radiocarbon. We had 104,000 years on this tuff in the middle, the tuff in member 3, and that's where that sequence of nicely bedded deposits was. And then at the bottom, down where the hominid comes from, we had, that is the hominid being early man, we had a date of 196,000 years. If you look at sapropels occur at 196, 172, 124, 104, and 8. So we had 3, the ones in purple, that fit, and we assumed that the others, we had 2 other disconformities in there, were 172 and 124,000 years. Now, it turns out that Well, I've dealt with Ian, you'll see him in a minute, Ian McDougall for years. Someone criticized his ages, and he said, Frank, we have to write this up again. We can't stand for this. And I want you to go over everything again, so I did. And in doing so, we found in the literature that after all of this was published, someone published a date on this tuff of 2 that should be about 172,000 years. And it's from a different place in Ethiopia, but it has the same chemical composition. It's 180,000 years. And that gives us even more confidence that our age on the earliest Homo sapiens that is yet known is 196,000 years in age. You see the outline of Lake Turkana there. The blue is with the expanded Lake Turkana, and notice that the delta, it's down at the north end of the lake now, had moved northward by over 100 kilometers simply by filling up that lake. And this is the time that sapropels form. So all the deposition was going on at Kibish. That has lessons for us later as well. Well, here's New York. There's a Watertown person here. Could point that out. That gives you an idea of the scale of Turkana in relation to New York, the Keystone State. Here's Kenyanthropus platyops. The type locality is here. This one's about 3.5 million years old, okay? Here we have 2 that I think you will agree are very different. The one on the left is Homo erectus or Homo ergaster, depending on your preferences. The one on the right with the big crest is a Australopithecus related to Boisei, probably Ethiopicus. No one has agreed on the taxonomy yet, all right? And then from the Omo, we have this wonderful, robust Australopithecine cranium, one of the nicer pieces that Clark Howell found during his expedition, okay? And the Kenyans are tremendously proud of these, and they have put these on their stamps. Right? So we saw that there was a connection between Turkana and the Mediterranean way up there, 3,000 kilometers away, but you will see that there are also connections between Turkana and the Gulf of Aden and now the Arabian Sea, about 2,000 kilometers to the east. And how do we get these connections? The way we get these connections is through these volcanic ash layers. That very light-colored piece of material there is a volcanic ash. The one up on the horizon is a volcanic ash. It turns out these are just about 100,000 years apart, and we have just 5 floodplains in between those. Again, we see the 20,000-year beat of the climatic cycle. All right? Now, the first thing we can do with these volcanic ashes, if we have pumice, because we can't stand any contamination of these samples, we take these pumices, clean them, scrub them, cut them off with knives until there's nothing left except the original material of the eruption. We separate the feldspar, and then we, after separating the feldspar, some feldspar contains potassium, and some of potassium is radioactive, that is potassium-40, and it decays to an isotope of argon, argon-40. So argon is a gas, and when things are hot, argon doesn't accumulate. As soon as volcanic material is cool, argon accumulates. So the more argon per unit potassium that you have in a crystal, the older it is. And this can be measured very, very precisely, all right? This is the guy that's done most of the work since 1976. This is Ian McDougall, now retired. He's 76 years old, and he started in 76. Ian McDougall from Australian National University, and he's done a yeoman's job at making sure that every date that we get is nice. Now, if you start at the top here, there are the 3 at Kibish. There's the radiocarbon date, and then the 100,000, 200,000-year-old date. Then we have something we can date at 750,000. We have something we can date at 1.23, at 1.3, at 1.35, 1.4, and so on. Those are all independent dates, and what is terribly important is, we've already said we have superposition. Each time we date one of these, the date falls where it should in terms of underlying and overlying units. And this gives us tremendous confidence that the dates are probably all right. All right? Now, these volcanic ashes are not easy to spot. They're easy to spot in the field, but you don't know which one you have. To do that, we've got to come back. For example, on the top there is a tuft that's called a Chari tuft. It's 1.38 million years old, plus or minus 0.02. It's 5 meters thick on the east side of the lake. On the west side of the lake, it's 20 centimeters thick. It's about like that. In both cases, it has big pummices. In both cases, you can date it. And it turns out to be compositionally distinct. The first way we tried to distinguish between these ashes, besides looking at them in the field, which certainly didn't work, was to look at their shapes. And you might say, okay, well, the two on the left are different than the one on the right, all right? The problem is there aren't many different sorts of shapes that you can use to distinguish these. So we started on looking at chemistry, and the bottom right diagram there shows you iron plotted against niobium. We measure some 20 or 40 elements, depending on what we need to know. And what you find out is that each of those volcanic, if you take just the glass, each of those volcanic ash layers is distinctive. They've got a fingerprint. And once we've fingerprinted those, and once we've measured their ages, we can carry them everywhere in the basin. So everything that's the same color in these three columns is in the same time interval. And Ian McDougall has put the ages on these time intervals. Now you notice that the intervals can be very thick of one color and very thin. That's because this is a tectonically active area, and so what is deposited in one place can be very different than what's deposited in another at the same time. Now I've spent nearly 30 years measuring the compositions of these ashes. We thought at first that there might be as many as 100. If you measure the compositions of these bloody things, I wish new ones would stop coming up. We've now got 356 of them in sequence in the Turkana Basin. If there were only half as many, it would be, I wish there was just one every 20,000 years, and that the one at the bottom was purple, and the next one up was green, and the next one up was pink, so we could tell them apart in the field. We can't. We've got to bring them back, analyze them, and then go back to the field with the new knowledge. So this is how we sort of jigger ourselves up. What you can do, though, is here is a very restricted period of time, 200,000 years, and you can divide this into very small pieces of time. This is in the Okote complex. If we needed to, we could give you an age within 5,000 years on anything in that sequence, and probably better one of these days. All right? What did I have up in the corner? Oh, yeah, these two guys that came out on the cover of Nature. This tells you the problems that the anthropologists have. The morphology of those two skulls is essentially identical, but the size is incredibly different, right? Now, is this male-female, or were there really two different sized creatures running around? Or was one poorly nourished and the other better nourished, and so on, all right? So here are some more of these wonderful things, and I will go through these quickly because I know I'm over. Here's Kenyanthropus platyops. I know that Tim White calls it Squishopithecus, doesn't believe it's different, but I'll stick with my colleagues, Meave Leakey and Fred Spohr. They do think it's different, and they think they have good evidence of that. All right. Well, what else can we add? Many of you probably know that the north arrow on a compass points north right now. But if you go back 800,000 years, the north arrow pointed south. That was called normal. That's reversed, okay? Now, we know the timings of these, and so we could measure all of the magnetic transitions, and we've done that in many sections in the Turkana Basin. And what you find out is that these fit beautifully with the dated units. And not only that, but in 1992, we showed that the existing chronology for these transitions was actually incorrect, and the first big correction came out of the Turkana Basin. So wherever you see a black ellipse there, we've measured the polarity, and those give us additional time control on these ancient fossils. We now have on average, that's actually better than that, we just got some more. But we can still go further, all right? Because these ashes exist in the deep sea, and if you want something independent, go to a different system. Go to a biological system where people have studied these microfossils That's a picture of a Millenia huxleyi there. These are little algae that make calcite plates, and they evolve very rapidly. So we could find out the age of things, of tuffs that is volcanic ash layers, in the Gulf of Aden, simply by looking at the ages of the calcareous nanoplankton that were being deposited when they were laid down. And this actually was the break for Hadar. Lucy is up there very near BKT2, all right, well above the Sidiacoma tuff down at the bottom. And this is something that made me very unpopular, but actually it turns out they like it now. It actually works and makes sense, right? If you're students and you're working with people, if you find something that you think is incorrect in science, you correct it, but you be nice about it. You don't have to argue ad hominem, that is against people, to say that, oh, this woman down here, Valerie, doesn't know what she's talking about, right? You don't have to be that way. You argue on the basis of the facts, and I can't give you any better advice than that. If it wasn't for that, I wouldn't be working in East Africa now, because when Richard asked me to come over and complete his geology in 1980, I said, why on earth do you want to have me work for you? Because I fought with you for 20 years now. And he said, well, the reason is that you never argued ad hominem. You always argued about things. And he said, secondly, you're right. So Richard knows how his thing. Anyway, this gives you an idea of the area over which some of these volcanic ashes are deposited. This is the Moiti tuff. All right, I don't know what's cut off up there. It goes all the way from the Western Rift all the way into the Gulf of Aden and way down into the Somali Basin. Well, these are subcontinental dimensions. You have the same thing here that came out of Idaho, all right? Now that we've dated all of these things, we find out that we actually got extremely good numbers by the 20,000-year clock, the precessional clock. We've now dated these independently on land, and it gives us tremendous confidence in the chronology. So here we have volcanic ashes that are correlated between sections that are several hundred kilometers apart. We have all of these ages, and what do we do with these things? Well, we put the fossils onto them. So you find out how the fossils are related to the ashes. We have from Ethiopia, Tim's wonderful Ardipithecus rhamidus. Then we have above that Australopithecus hanamensis that Meave found. The Turkana Basin is its principal source. Above that, Kenyanthropus and Australopithecus afarensis. Australopithecus gari, higher than that. Notice here that almost every time, this much I will say about these, almost at any time in the past, except for the present, there is more than one kind of two-legged creature running around on Earth that's rather like us, all right? And it's only at the very end of geologic time that we come down to a single species, which is Homo sapiens, and all Homo sapiens are quite closely related, all right? So to sort of put it into a long-time summary, you don't have to make too many changes. Luca, you may have heard of. Luca is the last universal common ancestor. It's hypothetical, all right? But it's at least 3,500 million years old. Nucleated cells come along certainly before 2,100 million years. And if Javot is right from her paper last year, they may be as old as 3,200 million years. We don't see much happening until you come to this the big Cambrian, Precambrian boundary at about 540 million years ago. But at that point, we have bone. And bone is one of our characteristics. To the bone, add limbs and 5 fingers. You go back and look at the old amphibians in the Pennsylvanians, they had 5 fingers. We've still got them, okay? So we had tetrapods. Add hair and mammary glands in the Triassic, and you've got mammals, all right? So how do we get to primates? It's really hard to say how primates are different than other mammals. We've got binocular vision, we've got nails instead of claws, all right? And we've got an opposable thumb in most of them, all right? So we get up to the primates. How do we distinguish us? We're primates that walk around at 2 feet. And this may have happened several times instead of one. It's the weirdest sort of locomotion. I mean, dinosaurs do it, birds do it, and we do it, and that's about it, right? You have, yes, things that hop along on 2 feet, but not things that go along on just 2 feet. And then how do we distinguish us? We're not really quite sure, as far as I can tell from the mess that the taxonomy of hominids is, but at least we have large brains, and we're very proud of those brains, all right? So rather than a single step in evolution, we're not coming from a bacterium to man in one step. No, we're not. Darwin envisioned many, many small changes, and our time scale is set by that of the Earth itself. So several of Darwin's predictions have been realized. Geologic time is very long, much longer than thought by scientists in his time. And many fossils of early man have been recovered now. I had to shorten this afternoon. I won't do it because I'll go on for 10 minutes. But probably the thing that upset people the most was the finding of Java man, because Darwin had predicted early man should be in Africa, and what does Eugène Dubois do? He goes out and finds early man in Java, all right? And it wasn't until it was 1888. 1924 was the first one from Africa, was Raymond Dart, all right? And then a principal source of information about our ancestry indeed lies in Africa, but Asia and Europe also have important records. Some of you may know of the Dmanisi in the former Soviet Georgia that has things that are at least 1.6 or 7 million years old, perhaps 1.75 million years old. And also in Europe, you have this wonderful Cima de los Huesos, probably the ancestor of the Neanderthals in Spain. Absolutely marvelous stuff, all right? So, what did Darwin say? And why should we worry about evolution? Why should it make us feel any littler? I think he said it best in his last paragraph. There's grandeur in this view of life, with its several powers, having originally breathed by the Creator into a few forms or into one, and that from so simple a beginning, endless forms, most beautiful and most wonderful, have been and are being evolved. That's a single use of the word evolve in Origin of Species. Thank you very much.